All right. We come back to our general convex problem domain. So in general, the problem we want to solve is minimize x0 of x such that phi of x is equal to 0, fj of x. So what did we do? In the previous class, we started to write something called a Lagrangian function or Lagrangian. What was that? L of. So what did we do really? We picked up our function. We wrote it as it is. Now we said, let's multiply a variable. We'll call this the Lagrangian variables. So for each constraint over there, fix and plus a mu j and j of x. So did I have to care about the sign of lambda i's and mu j's?
Lambda is part.
Okay, and why should that be the case? If I want it to be meaningful in the way I did that, so what I want to really show that the Lagrangian so when I'm writing lambda I and mu j, it's for all i's and all j's. I could technically just write it as just this. And if I were to minimize this with respect to x, what do I want to show? I want to show that this is this way or that way. I want to connect it to the optimal answer. And that is my f0 of x star. Right? So if I want a connection, what should I expect first of all? Should I expect something like this? And for that, I need lambda i's to be greater than or equal to 0. Otherwise, I won't get this. We came until so far. So it's very important to remember that the multiplier with an inequality constraint has to be greater than 0. This time we don't care because this is an equality constraint equal to 0. So that won't matter. But this one is very important. That keep that in mind. So far we came 2 classes ago. The point is, what is the physical meaning of doing something like this? What are we trying to do? We had these very strict constraints. We suddenly lost all the constraints. And now we are thinking about this is just a unconstrained problem. Because given that this is true, I could just try to maximize this with respect to lambda and mu. But why do you think there is something nice going on? By removing all the constraints and moving them to the objective function. That's what we really done. Is it an intuitive understanding of what is going on here? So can you write this problem in this form exactly? See, this is only a floor bound. Can you write this form where the optimal answers will actually match? How you write it is your problem. That's part of the question. But can you write the constrained optimization problem as an unconstrained problem with appropriate functions where the optimal value will be identical? For the moment, what I have done, that's not true. But is it possible to write it in such a way that the optimal values will be identical?
The maximum over lambda.
No, it need not necessarily involve. See, lambdas and mu's are artificial constructs for the moment. All you are really given is F0, F1, Fi's and edges. Lambdas are not given to you. I am just constructing this in between quantity. So those are artificial things. So instead of them, what else can we plan and try to claim that I'm not saying it's easier to solve or difficult to solve. All I'm saying is, can you reformulate the original problem in such a way that all the constraints disappear? So think about a new function, which is simply a function of x, which is minimize over x,
If
f0 of x, or my notation is typically 1. So this is my indicator function. So can you put some indicator functions and say the solution here will be identical to the solution there?
Fi of x less than
Okay, so indicator. What does it mean? An indicator.
h I j equal to 0.
Yeah, what does it mean?
So whenever whenever if xi is less equals to 0, it will give you 1, except and other set in whenever for which values of x if xi greater or equal to 0, greater than 0, it will give you a 0.
That won't work. Then those two minimization problems are not equal.
You are adding you last class.
Forget about the last class. I'm trying to say this is one way of doing it. That's called a Lagrangian duality. What if I wanted to write it exactly? This is all I'm getting is a lower bound. That's all I've got. If I want to, I'm not saying you can solve this easily, so you can solve that easily. I just want you to reformulate. So what do you want? When the constraint is not satisfied, what should happen? You want the constraint to be satisfied. So if the constraint is not satisfied by something, what should it put? What's the only value this function should take when the function is not satisfied? That's the only choice, right? You're trying to minimize this. If somehow this function is such that whenever the constraint is not satisfied, it takes a value infinity, that's never going to be picked up as long as there is at least one point for which the constraint can be satisfied. So as long as the set is feasible or set is non-empty, you're going to get a non-infinity, like a bounded value. So this function should really not be called indicator. Indicator just
Or can we just divide it?
divide by what?
F not x. Divide both the indicator values, the product of both the indicators.
This is the first one. Okay. What do you want me to do?
Divide the product of both the indicator variables
Mhm.
to F naught of x.
I don't understand. Forget about the second. Why do you care about the second one?
Like if we want to rewrite the same problem,
Yes.
then that will be minimizing over x,
Mhm.
F naught x divided by indicator Fix less than equals to 0 into indicator Hjx equals to 0.
You're making it much more complicated by multiplying certain things. They were nice and separate. Now you're combining them. Instead, it's much easier. You just to define this function such that it takes a value 0 for any point x which is feasible and takes value infinity for all other points. Similarly, it takes value 0 when it is 0, otherwise it takes value infinity. Ideally, I would have liked. So let me just use this space so that we can compare what is going. So one, let's call one fi of x is equal to 0 if fi of x is less than 0, infinity, otherwise, and one j of x equal to 0, jx equal to 0. Okay. Now, this is an exact, it's the same problem rewritten. There's no change. Now compare this with this. Now they're comparable. Anything wrong there? The definition, there is a problem. So this should be written as fi summation over I, summation over j x and hjx. Now they're comparable. Now compare what did I really do by going to the Lagrangian. They're not identical. This is what I would have really liked to do if it was feasible. Indicator functions are highly problematic, so I can't really do them. So I'm doing some surrogate function of that is what is coming in to the Lagrangian. So what is the relationship between lambda I times fi of x and the indicator fi of x? If you want, sorry, what derivative? This product is essentially counterpart is here, this counterpart is over here, right? So why do you think we are getting an inequality of this type? That we are getting, that much you have shown. Big duality. Not clear what's going on? Just compare the indicator function with this function for a fixed I. What kind of function does it look like? Let's plot it, assuming it's one dimensional. So this is my x, and let's say this is the boundary of fix crossing 0. So below this it is 0, above it is greater than 0. This is fine. What kind of function is indicator? It's just suddenly from 0 just goes to infinity. And what kind of function is this one? The other function, sorry? And lambda is greater than 0. So it's below and then remains below, right? Potentially going to infinity if it's increasing. Now can somebody tell me what is the relationship?
So that indicator function will always be greater than equals to.
Okay. So what? That is true. Just by inspection. That in fact, lambda I f of xi is always less than equal to the indicator fi. That's essentially what the connection between the two is. But why is it helping me in any way? I wanted such a strict penalty. I'm giving you much softer penalty. Right? My penalty should have been as soon as you go become infeasible, it should have just suddenly gone to infinite. What have I done instead? I've given you a very soft penalty, which is even linear in some sense. So why should you get this? Just look at this, right? With such a strict penalty, what's going to happen? And with a very mild penalty, what's going to happen? Milder penalty should lead you to
Limit lambda goes to infinity.
okay, fix a lambda. Doesn't matter.
Okay, so the bigger and bigger lambda will get the.
No, fix a lambda. Any lambda, this is okay, right? We have not said this is true for any special choice of lambda as mu's. As long as lambda is greater than 0 and mu is anything, this is true. So you can fix a lambda and mu and make an argument that why should this be true by comparing these two.
If we fix the lambda,
Yes.
we want to look for minimization, right?
Yes.
So we want to take the x towards minus infinity.
Okay. That depends on the function.
Yeah, but by the choice of function that you have to draw.
No, that's not true, right? It depends on f0 and fi is x. I could just simply swap the function and take it to plus infinity. So that's not important. Plus infinity.
What x tends to infinity?
It's not important. You're specializing it for certain functions.
So, say since there are feasible solutions, there are constraints which cause fi of x to be negative. So f naught of x star, L of x star will be 0 of x star plus some value of some positive value times fi of x, it is less than equal to 0, and at day is 0. So at that point, this minimum of L.
No, we already know weak duality. Why are we getting it is the question. I don't want any expressions here. That we already established. The weak duality has been established. The bottom formulation is exactly equivalent to my original formulation. Point is, what was the motivation to do all this? Here there is a very strict penalty. There is a milder penalty. So why should milder penalty give you anything? Just compare term by term if you want to. So what is this? This if I were to put a minimization right here, f0x is this identical. Lambda I times fi of x compared to this indicator function. Just pick up for any one fixed I. What will this enforce and what will this enforce? Which value will be smaller? As simple as that. That's precisely the reason. It's just giving you a milder penalty. Just think about somebody giving you a lower punishment compared to a higher punishment. Which one would you prefer? Lower punishment. And that's what exactly is happening. So that's why the value of this is higher than, sorry, this value is at least so much. The penalty will be at least so much because I have made it milder. If I had tightened it further and further, I'll just keep moving towards my fx star. See, this is equivalent to my original problem. I've somehow, I don't want to call it relaxed, but that's what is going on. I've relaxed the problem. I've given you less penalty for violating things. And in the process, I've got only a lower bound. As I keep increasing lambda towards infinity, this precisely will keep moving towards f0 of x. Because as soon as you violate, you get a product which is positive. But then it requires choosing the appropriate lambda. But for any fixed lambda, this is true. And this is nothing but that the linear penalty is a lower bound, is an underestimator for the actual bound. So just good to remember how we even arrive at something like this and why this is actually true. Expressions, of course, they're all true. It's good to know what we are doing. And now with this dual, we'll come back to our good friend, which I indicated when we came to all the conjugates. So this is what the real utility of learning or working with conjugate is, because in the dual, it will just appear naturally. Okay, so let's start with certain simple examples. To minimize x transpose x such that Ax equal to, what will be the dual of this? What is my Lagrangian? There is only one constraint, so lambda disappears. So I want lambda here, I just want mu. This is just a convention, you can call that lambda. This is x transpose x plus, rather I chose mu, right? So mu times x minus 2. Right? Okay, how should I proceed further if I want to find inf of this with respect to x? Yeah. So I want to find inf of respect to x comma mu. What kind of function is L? It satisfies all the properties that we need to show that the derivative is sufficient to find the optimum. It's in that nice form. I'm saying it's more than convex. It's a strongly convex function. So it is equivalent to find this, or finding x star is just to equate this to 0, which will imply as 2x plus mu times a equal to 0. So we get x equal to mu a by 2. And putting back, what do we get? So this function is called g of that. So there is no lambda. It's called muscle memory. Even if you want to, you can't get rid of it. So x transpose x, when this is true, I'm just going to write it from here. Minus 1 by 4 mu transpose a transpose mu minus b transpose. Yeah. This is my dual function. Any observations to make here?
Minus mu.
Which one? Yes. This is 4. This is correct. Yeah. What kind of function is this? Linear. Linear in what? It's quadratic, right? It's a function of mu. And this is not quadratic. Is it concave? And is it an accident that it's concave function? Taking the max of. You're not taking a max of anything yet. How did I arrive at g mu? G mu is nothing but infimum of the Lagrangian over x. I've not taken any max yet. So is this an accident that g of mu is concave, or it's always going to happen? What kind of function is L of x comma mu?
Convex.
Convex. And we're taking infimum of convex functions. We proved something. Did we? Okay, so forget if you don't remember anything. Is it an accident that this appears to be concave? This is clearly concave. Because without the minus, it is convex. So with a minus, it's concave. So anybody wants to make a bold claim that g of mu or g of lambda mu is always a concave function? Sorry?
The infimum of the convex function is unique.
Okay. But we're interested in as a function of lambda comma mu. Nobody wants to guess.
You have done something. Just let me just. We have a convex set. We have a plane, and we are looking at a distance. Uh, uh,
Don't specialize it to this function. Okay. For this function, we clearly know what it is concave.
no, you have done that from a point.
Yes.
Given a convex body, if you have a point outside of it, and you are looking at a distance.
Okay.
Distance function. It will from a line from each point from the distance of the minimum distance of the convex body, that curve that will get, that is a convex concave basically.
Okay, keep going. So I don't think I hear an. Anybody wants to guess? Yes or no? Possibly for special functions. Okay, so just to so x of lambda is f0 of x plus lambda f1x. Let me just put it for 1. It doesn't really matter. Mu of h1 of x and g of lambda mu is inf of x comma. Okay. Now the domain of G is, what is the domain of G? Lambda comma mu, such that G of lambda mu is greater than minus infinity. Okay. Here, domain of G is a convex set and G of lambda mu is concave in. Sorry? You're giving proof?
Huh?
Are you giving me a proof?
No, I'm just asking that it is the idea. Like we are.
No. First, at least absorb what is being said. Then we'll worry about the proof. What is the domain of G? All points for which the value is not minus infinity. Okay. What we are going to show that domain of G is in fact convex, because that's what the set we are going to maximize this over. If the set is not convex, I've only created a bigger monster for myself, right? Because all we know is what is the convex problem? Minimizing is equivalent to maximizing a concave function, but the set underlying set better be convex. There's no underlying concave set. Okay, so convex set, and this is concave. And thankfully, the inequality I'm going to use will also tell you that some of you made a mistake in the writing the direction of the inequality in the homework. Some of you, not all. We'll come to that. Okay, so any idea how to prove this? Let me do this for just lambda, forget the mu's. It makes it much easier to handle. Everything will go through. So assume that mu is real. There is no equality constraint. So let lambda 1, lambda 2 belong to domain of G. What is L of x comma alpha lambda 1 plus 1 minus alpha lambda 2? This is a linear function, right? So what is this equal to? Alpha times L of x comma lambda 1 plus 1 minus alpha times L of x comma lambda 2. So far so good. Now throw in the infimum, because that's what the function G is. So with the infimum, what inequalities are there? Inf of f plus g. So let's just go to that. Infimum of f plus g and inf of f plus inf of g. Which direction does the inequality go?
Left hand side will be greater than.
Everybody is fine with that? Can you give me an example? When f is equal to x and g is equal to minus x, what happens to the left hand side? I just want to make sure that I'm not making a mistake. Yeah. And what is the right hand side? Why? What if my set is x greater than equal to 0? I'm infimizing over x greater than equal to 0. Now what happens? F of x is x and g of x is minus x. So what's the left hand side? What's the right hand side? You still get minus infinity. How? Okay, so then this is the right direction. This is just to double check that we get this right. I think somebody in the homework reversed it and proved something. Just see, I pointed it out. Okay, so now if I throw in the inf, what will happen? This will be greater than equal to inf here and inf here. Now inf over this is what? G times alpha. Or let's call it, make it more specific. Alpha times g of lambda 1 plus 1 minus alpha g of lambda 2. And what is this quantity? G of alpha lambda 1, 1 minus alpha lambda 2. So this is already shows that the function is concave. How should I prove that it's a convex set? Using this. So this conclusively proves that the function g is always concave, irrespective of f being convex or not. And not use the fact that f is convex. So this is something very important. Another advantage of solving the dual. So even if your primal is not convex, you go to the dual, that's always concave. So you can always solve the dual problem as long as you show me that the domain is convex.
It is linear.
L is linear. So that was the equality. I have skipped one step and put on top of it. I had only that much space. So that's the advantage of recording a video. This will all show up that it was equality and then it became inequality. So this is a convention. I don't know if you guys know this. Once I write an inequality, the next one I write is equality. I don't keep writing it inequality because this is equal to this. So eventually, if you put together everything, that will still remain as inequality. That's just a standard notation. Just to denote that in each step, am I loosening it or not? So if I keep writing it equality, then these two things are identical. So now I claim that I've also proved that domain of G is a convex set. How? Pick any 2 points which are in the domain. G of lambda 1 is how much? Greater than minus infinity. G of lambda 2 is how much? Greater than. The sum on the right hand side is greater than minus infinity. Sum done. So proving concavity actually gives you that the domain of G is a convex set. So yeah, remember, this is a very important fact that irrespective of f being convex or not, G is concave. L is linear. What is L? L is f0x plus lambda f1x. Forget about this one. Okay. So what is L of x comma lambda alpha 1 plus this? I can just throw in alpha here plus 1 minus alpha. Just split it. Don't scare me.
Linear on the second.
Yeah. That's what I'm interested in. So this was not an accident that your G function turned out to be concave. Every time you'll get it. And if you're not getting it, you're making a mistake. That's one check. If you're coming up with a dual whose objective function doesn't look like concave, you made a mistake. Okay, so now let's just directly jump to. So the book keeps going around and now. So just directly write that. Okay, so now we can get some examples in what it will look like. So something we did last time, essentially an LP, so C transpose X minimize subject to X equal to B and X greater than equal to 0. We know a lot about this now, but let's just apply our Lagrangian duality and see what dual do we get. So what will be the function L of X lambda? Mu should be C transpose X plus lambda X plus mu times AX minus B. Now these conjugates will appear naturally. So when I infimize L of X lambda mu, how do you think the conjugate will appear naturally here? What should I combine and say, okay, this is the conjugate of some function? hopefully you remember what the definition of f star of y was. Y transpose x minus f of x sup over y. Does times it allows me. What do you think is going to appear here?
Yes, your implied condition on this side equals to 0, right? Right now, the implied that is exactly x is
You put a minus x less than equal to 0.
yes. And
So I will change the inequality, but it's, yeah, fine.
so if we take a minus out,
Mhm.
then minus of int is basically so.
I can always put a minus, right? It doesn't matter lambda is minus or not. I should correct, I agree, but that's not the problem. Like, if you've seen what is going on, that should not matter. So what you want me to do is to write a minus, I'll write a minus. Why? Because it's written as x greater than 0, while the way everything was set up was x less than 0.
But you want, so basically in the previous to go to the optimal answer, we have to take the value of lambda larger and larger.
You're not doing anything. All I'm saying is, how is this going to appear? What is inf of L going to look like as a function of some f star of something? That's all. I'm not asking you to solve the problem. Somebody?
Greater than equal to that star of minus lambda, lambda minus minus.
See, what are all the common terms to x? I'm trying to infimize over x. What are all the common terms? C transpose minus lambda plus mu a. This is with an x. And what is my minus mu b? If I wanted to do something like this, what should I do?
The f is constant mu, then this will be less than equal to h star of the
Look at this form. Something is appealing, sitting there as it is. What should be my f of x here? Maybe let's just do it more generally. You're getting confused. F0 of x, fi of x, or f1 of x less than equal to 0, and h1 of x equal to 0. What is else? X lambda mu is equal to f0 of x plus lambda 1x plus mu times. Okay. Now try to infimize this. So g of lambda mu is inf of all of this. Okay. Now where does the conjugate appear? So take this as x greater or minus x greater than equal to 0 and take it as x equal to. Hopefully you should see this. What will happen for this case? What's the problem? What's the problem?
If the fx as f naught plus mu h1x.
They do it for this. Don't worry about everything.
Can go to previous.
Which one?
Space.
You're having trouble there. It's okay. Just do this. So what will, for this particular example, what will this be? Inf of f0x plus lambda
Minus x plus mu a x minus b.
okay.
So if I the linear
What is
is not
everything we have
linear, so we are taking, as you said in the last part, last x, that coefficient of x term we are taking together.
take whatever, just tell me how the conjugate will appear. Do whatever you want. The AC off, but I'm the only one feeling hot. Now, let's go back to the previous example. What should I do with this? Forget, supposing you did not know this. What is the answer here?
So y transpose x will be mu and rest of them with x.
Sorry,
Y transpose
forget about this.
f of x will be exactly the first one.
It doesn't even exist. Just tell me what the answer is. So when is this non-trivial? The answer.
Okay, the sum is non like greater than.
Right? You take plus, I will drive it to minus something. You take minus, I will drive it to minus. The only way there is a non-trivial answer is when this whole term is 0, for which the answer is minus mu times b. So what is this equal to? Minus mu b when ct minus lambda plus mu a equal to 0 and minus infinity. Otherwise, so can I get my usual dual from here? So far, so good. How do I get back my dual? This is my primal. What is my dual? And remember, lambda is greater than or equal to 0. That is a constraint here. Why are we not done yet? All we have to do is to maximize this while respecting the constraint. Right? You got our g function. And what's the dual? It's just to maximize minus mu b subject to this constraint that lambda is greater than or equal to 0 and C transpose minus lambda plus mu a equal to 0. There's nothing else left to be done. Something is missing. Should we go back to the first slide? This is true for every possible value of lambda and mu. So this is true for also the maximum with respect to lambda and mu. That's my dual. Okay, now let's come back to this and try to do this for this is also actually not bad. Why are people not able to find some conjugate out of this? Conjugate of what? How should I write this so that I can bring it out as a conjugate of F0 itself? Can I do that?
Confused in the last part.
What confusion is that?
So in the dual,
What's wrong with the dual?
so the variables now is mu.
Yeah. And lambda. You always have as many constraints as you have, that many variables you are going to find in the dual.
Yes, but when you formulate that Lagrange, you said you focused on lambda equal to 0, but you don't care what mu means.
Yes, so I didn't care about mu is here. I'm not putting any constraint on mu being less than, smaller than. Mu is unconstrained. All it has to do is to satisfy this constraint. That is all. This is, you're okay with that, right? That this is not going to have any infinite, any non-trivial answer unless this is 0. So that constraint is enforced. So now where is the confusion?
Some inconvenience happens or
That you go home and find out. Okay. What about this? If I were to pull out a conjugate of F0, what will that be? Just take out terms which don't involve F0. That won't work, right?
no, like I mean, to make some adjustment.
Okay, make the adjustment.
We're looking over X.
Yeah, that is correct. Keep going.
We have to calculate the superior center.
But that's easy job, right? All you have to do is to put a minus. So that's not a problem. You can put minus from the outside.
So we have 0 star of lambda plus mu.
So let's first put a minus, a soup over X. What else?
Lambda minus mu times X.
So mu times B is outside. So I will not even worry about it. Now F0 appears with a minus. Right? What else remains as a function of X?
Lambda minus mu.
Lambda minus mu A. Okay, so it's already there. Now, why is that not in this form I am interested in? So what is this quantity equal to? F0 star evaluated at lambda minus mu A. So this is how they're intimately connected. So as long as your X, so now all you have to enforce is lambda minus mu A belongs to the domain of F0 of star. And that is what the constraint you will actually end up getting for your dual. So the final answer in the dual would be maximize, what is the two terms? minus mu b and a minus of f0 star evaluated at lambda minus mu a, where lambda minus mu a belongs to the domain of CS. This is how intricately your conjugates are dependent. And that's why it's so useful to know what the conjugate of a function is. Right? All right, so let's go to something which will be useful to you for your rest of your life. It's that universal. Everybody knows this just by the name. So they are called something called a KKT or complementary slackness. So we did complementary slackness for linear programs last time. Today we'll do it for general convex programs. So complementary slackness first. Suppose there is strong duality. So somebody tells you that the problem you're looking at has strong duality. That is, the optimal solution of the primal and the dual are equal. There is no duality gap. Then we are going to establish certain conditions. Let X star be primal optimal. How to do, like, how to establish there is strong duality or not, that's a very complicated problem. We will get some sufficient conditions next time. Under what sufficient conditions there is strong duality. But you can have all sorts of nasty problems having strong duality, which don't satisfy that property. So it's not necessary. X star be primal optimal and lambda star mu star be dual optimal. So what does it mean? That f0 of X star, you guys do this, g of lambda star mu star. What should be the relationship between the two when there is strong duality? I heard two different answers.
Strong duality then is equal.
Yeah, that's the whole point. Okay. Now, what is by definition? This is equal to inf over x L, where L is nothing but f0 of x plus lambda star f1x mu star right. Now, what is this quantity with respect to X star? If I were to plant X star here, what will happen? Yes. X star, remember, is primal optimal. That also means it is feasible. So this quantity is less than equal to 0. This quantity is 0. And what about f0 of x and f0 of X star? It better be that. So this is less than equal to how much? f0 of X star. Okay, what has happened in the process? Are you okay with that inequality? Now try to infer what this inequality tells us. We did something very similar last time for the linear programs. So what we have shown is f0 of X star is less than equal to f0 of X star.
of x star is 0 or lambda star is 0.
Okay. Mhm. See, there's something I missed intentionally. People are catching one inequality I missed in between. What did I not write? Which I should have written.
Inform is less than equal to g of x star, sorry, L of x star lambda star.
So this is right. How did we arrive at here? This is greater than 0, we know. Sorry, greater than equal to 0, we know. F1 of x is less than equal to 0. So this guy doesn't matter because h1 of x star is 0. So what is the next inequality I should have written? If this is true for all x, right? So this is less than equal to. So let's just erase this. Right? Because this is infimum is always going to be smaller than any one particular value. Okay. And now using the property that this is greater than equal to 0, this is less than equal to 0, this guy is anyway 0, this is less than equal to f0 of x star. So what does it tell us? It tells us that this inequality over here is actually equality. Because where we started from, we ended up at the same point. And what's the only way you can do that? That this product better be 0. So what happens? Either lambda star is 0 or the constraint is tight. That is what is called as complementary slackness. So if the strong duality holds, this is what you get. So implication is strong duality implies lambda star f1 x star so if lambda star is greater than 0, then f1 x star is 0. And if it is strictly negative, this is easy to understand that the constraint is not active at the point where the optimal is being achieved. So the Lagrange variable should have no impact on it. This is what it means, right? At the optimal point, that constraint is not even active. You're strictly inside because it is strictly less than 0. So having it or not having it should not matter really. That is why the particular variable, corresponding variable, should not have any impact. The other one is slightly more interesting. If lambda star is greater than 0, it automatically means the constraint is tight. So this is called complementary slackness. Very useful property. But before that, you have to establish that there is strong duality. Okay. So now let's go to, so KKT is, hopefully I'm getting, first name is Karush. There are lots of dots and all. So Kuhn and T is Tucker, all giants in the area. Okay. So again, under strong duality. So necessity requires strong duality. Sufficiency doesn't require. So if strong duality holds, then the following conditions are necessary. And now it requires that the functions are differentiable. This is just the feasibility conditions. They're also thrown inside the KKT condition. The important ones are this lambda I star. That's also so lambda I star fi of x star is 0. And the final condition is in fact our gradient condition, then del f0 of x star plus lambda 1 f1 of we've seen 1, 2, 3, 4 already. Why is this true? Number 4 is just complementary slackness. So both lambda 1 and mu1 are the starred versions of it. The setting is clear, right? X star is optimal for the primal, lambda star mu star is primal for the optimal for the dual. Then these conditions hold as long as strong duality exists. Strong duality is only actually telling you complementary slackness, which I proved in the previous slide. So why is the final condition true?
The gradient of everything.
Yeah, go on.
I'm taking the this one of the L.
Okay.
That
But
minimum.
why at lambda star and mu star?
I need to find that extra lambda star. We need to find x lambda and use such that L takes its minimum.
I don't know. You say mixing up things. So you're given this x star is optimal, primal optimal, lambda star, mu star is dual optimal. Now, are you claiming that x star minimizes L of x comma lambda star mu star? So think about the following, that given that X star is primal optimal, lambda star mu star is dual optimal, does X star minimize L of X comma lambda star mu star? If it does, then this is just the first order condition. This is exactly the first order condition for X star to minimize this. Are you saying this is true? Minimize. Yes, don't get confused. We wrote this in the previous slide and nobody objected.
Yeah, the L X lambda star mu star is less equals to X star.
Why do you have to go all the way? What does it even mean? What did we write on the previous slide? What was the starting point? F0 X star is equal to G of lambda star mu star is equal to inf of this. What is the inf? Is X star. So it better be the same thing. So in fact, this is true. And that's just the first order condition which is written there. So this is the necessary condition as long as strong duality holds. Now we'll say it's sufficient to claim the strong duality holds. So if you can show for a particular problem there exists this, then you are actually done. So all you have to produce is a pair X star, lambda star, mu star, for which all these conditions are satisfied. And we'll claim that that implies you have strong duality. Okay, so anybody wants to take a crack at it? Now you're given that there exists X star, lambda star, mu star. You want to claim that these X stars and lambda star, mu stars have this. The first three are just the feasibility conditions which are necessary. So keep that, that's required. So that is fine. Essentially, you have to use the bottom two. If you're getting confused by X star, just replace star by any tilde or something. Because currently we have a candidate which satisfies this. We are not shown that they are actually optimal. But it's just a notation sake. It's clear what we are looking for. There exists X tilde, lambda tilde, and mu tilde which satisfy this relationship.
Second, fourth, and fifth will get the delta F0 of X star is 0.
From 2, 4, and 5 imply
gradient F0 of X star is 0.
Let's call it tilde, just so that we don't confuse ourselves. So the pair here which satisfies is X tilde, lambda tilde, mu tilde, which is satisfying 1, 2, 3, 4, 5. Okay, so 2, 4, 5. This implies. Okay, that much is fine. See, what do you really have to do? You have to produce or show somehow that G of lambda tilde mu tilde is equal to F of X tilde. As soon as you do that, strong duality has been established. All you're looking for a feasible primal feasible dual for which the value is the same. Weak duality already tells you you're done. So that's all you have to do. So this is true. But what is G of lambda? Let's just do that, right? If you want to do that. So what is G of lambda tilde mu tilde? By definition? Just use this. What does it mean? If this condition is satisfied, it means that, let me write in English, is can you say what it means? You have x tilde and is satisfying this relationship. So for a fixed lambda and a mu, x tilde is minimizing this. That's what it means. So what can I write G of lambda tilde as? L of can I write this? X tilde, just replace star with a tilde. X tilde minimizes L of x comma lambda tilde mu tilde. That's what is coming from there. So inphi is replaced by just pushing it x tilde inside. Now what is the definition of this? F0 x tilde plus lambda tilde f1 of x plus mu tilde h1 of x.
That was the final conclusion.
Now x tilde happens to be feasible, primal feasible. So this is, but I actually given something even more.
Yes.
I'm given 0. So this I can strike off. Similarly, this being feasible, I can strike off. So what do I get? I produce a solution which is x tilde, f0 of x tilde is equal to G of lambda tilde mu tilde. And that is sufficient for me to claim that I'm done. So the proof is actually 2 lines. And most of the time, when you look at a convex program, you'll be doing this. If there exists a solution here, you're done. That's the beauty of all this. Hope.
Necessary condition.
No, this is sufficiency.
Okay.
Necessary was if there is strong duality, then necessarily this has to hold. Now we are doing the sufficiency part. Suppose there exists a triple x tilde, lambda tilde, mu tilde, which satisfies this, then that triple also has to have duality gap of 0. You have a question?
Yeah, if x tilde minimizes L,
Hmm?
how do you do that? Because gradient is 0, doesn't.
All of these are nice convex functions. That's why. Differentiable convex functions. So differentiability is there. L we know as a function of x is convex. As a function, no, as a function of x, it's convex. So that's why gradient is sufficient to do that. So hope I not tricked you because I didn't want to rewrite all over it. Take stars from the sufficiency type. You just take a triple which satisfies that. Okay, so let's do one example of how this plays out for an interesting problem. This is my favorite. If you're a communications person, this comes up all the time. The answer will be what is called as waterfalling. So I'll tell you the motivation. The motivation might not be there. So suppose you have n parallel communication channels, telephone lines, and the gain on each line, what is the gain written? Alpha I. Okay. So alpha 1 is the gain on each of these lines. So if you put, let's say, pi amount of power, P1, P2, and so on. So this is the resource you're spending on communication channel number 1, whose gain is alpha 1. The output you're going to get is logarithm of 1 plus alpha I pi, I going from 1 through n. Sorry, gain. If you don't understand, this is the function, output function, utility function. So this is given to you, that these communication channels have respective gains alpha 1, alpha 2, so on. You have a total power constraint pi less than equal to capital P, that you can spend over all these n channels. If you spend power P1 on the first channel, the resulting utility you're going to get is log of 1 plus alpha 1 P1. Similarly, log of 1 plus alpha 2 P2. And your resource is less than equal to P. Now, this problem, the answer will look like water filling, and the answer we get is from just applying our conditions. So, what those conditions will mean? Essentially differentiating and equating a lot of things to 0. Okay, so what is log of 1 plus alpha I pi will look like? 1 over. So, I'm just taking the derivative. So, let's write L of pi or vector p comma lambda is simply summation log 1 plus alpha I pi plus lambda into summation pi. All right. Now take the derivative of L with respect to p. Pi, each of them. What would be the resulting answers? Sorry?
Minus.
Yeah. All right. So this will give you 1 over 1 plus alpha I times alpha I and a plus lambda equal to 0. Right? So for each pi, I'm going to get the same condition. And what is the constraint on pi's? Using that, I'm going to solve for it. So lambda is equal to minus of alpha I over 1 plus alpha I pi for all alpha. And what do I know? Summation pi is less than equal to p. You can argue that this will be actually equality at the optimum, because if you spend little less, you're only going to get less. So at the optimum, it will be equality. So all you do is you write this in terms of pi as function of lambda. What will that be? So pi is minus alpha 1 plus alpha I pi. So pi is minus alpha I minus 1 by alpha I. So I'm getting all sorts of negatives. I should not have got that. Answer I'm expecting is 1 by lambda minus this. So somewhere did I start with a wrong lambda? One transpose x, that is okay. Okay, so pi also greater than 0. That's okay. The way they have written is this is made to be equality, which is okay. I have to do a little bit more work. So allow me to do this minus, and you can look at the book. Essentially, this will appear with a minus. The answers, if you this will essentially end up being plus a plus a plus. Okay.
Where are more constant than the Lagrangian chain?
I agree. So for the moment, I'm not doing everything, but it will end up exactly like this. So all I wanted to indicate is what is this? It's telling you that each answer, Pi, is some fixed threshold, which is given by 1 by lambda, minus if alpha I is large, is going to give me larger power. So if alpha I, the gain is larger, so alpha I large implies Pi large. That we should have expected. But what is happening is all of them are getting subtracted from a particular fixed threshold. So what it looks like pictorially is the following. That let's say this was alpha 1, this was alpha 2, height is what the value is. This is alpha 3. And let's say I'm going to close this off as just 3 channels. What is answer is going to look like is, depending on the total power you're going to consume, this is my threshold 1 by lambda, which will be decided by the total amount of power given. And the actual power dedicated for each channel is going to be this value. This is the difficult part, where that's why you need that condition that Pi is greater than or equal to 0. It can happen that the total amount of power available to you is not sufficient to give non-zero power to each of the channel. So what you will do, as soon as that happens, you essentially throw this out and reassign everything so that these 2 channels are the only ones which get the power. So that's why it's slightly tricky. So you have to maintain that constraint that Pi is greater than or equal to 0. Otherwise, an answer will look like of this type, where Pi will be actually negative if you don't enforce that. And once you enforce that, these bad channels, these are essentially bad channels which are, okay, sure. So this is 1 by alpha 2. These are the bad channels which are high. And those ones will be eliminated and you'll get back to the places where you can actually put positive power. So it's in the book, just look at back. But answer is this. And what I wanted was the interpretation of that. And that's why it's called water filling. So as if you're putting towers in a bucket, and you're pouring water at a particular level. The level will be maintained. Anybody who is above the level will get nothing. People only below the level will get actually something. Because water will not stay here. It will fall off. That's the point. That's why it's called water filling. And it will stay here only if the level is above it. So if there is sufficient power to invest, then only it will give it to bad channels. That's the way. Okay, let's stop here. Your homeworks are here.